So the binary number system. Computers see things as ones and zeros. In other words, in binary. Now, decimal numbers which we as humans work with consist of the digits 0 through 9. So in other words, if you think about it, binary is a number system that consists of two digits, 1 and 0, where decimal numbering has 10 digits from 0 to 9. Now, specifically, host servers and networking equipment actually use binary addressing to identify each other. So even though we see an IP address in decimal, computer devices actually see them in binary. Now, each IP version 4 address, so for instance, that we see, we've seen that it's actually subdivided into 4 sections. These sections are octets. So each one of those 4 numbers in an IP version 4 address is called an octet. Now, every octet is the same as saying it's a byte. Now, a byte is 8 bits. So in other words, an IP version 4 address is actually 4 bytes or 4 groupings of 8 bits separated by dots. So in total, an IP version 4 address is 32 bits long. Now, if we take a look at this, it shows it a little bit more clearly. That is an IP version 4 address. So 192.168.10.10. That's the way we see it. But a computing device will see it as 4 separate binary bit strings, each being 8 bits in length. And it actually uses that bit string to make decisions. So you will learn later on that we can figure out what the network address is of an IP address. We can do that via calculations, but we tend to do things in decimal. Your networking equipment will perform everything based on the binary. Now, this chapter or module contains a few calculations. In fact, there are a few calculations when we get to IP addressing in later modules as well. The problem is, for the Cisco curriculum, for all of the Cisco curricula, in fact, you are not allowed to use any calculators. So for any of the calculations that you do, it's all up to you and a pen and a piece of paper. So before we get into binary, let's first take a closer look at decimal. Now, both binary and decimal make use of positional notation, meaning that wherever the digit is in the sequence of the value, it presents a different value according to its position. Okay, so what do we mean with this? This is a decimal number, 5,706. Now, in primary school, you are usually taught that you have the ones column, you have the tens column, the hundreds column, the thousands column, etc. That column structure actually refers to the positionality of the various digits. So let's see, what do I mean with that? So in computing terms, we start counting from 0. So the ones column is our first digit. In other words, digit 0. The tens column is digit 1. The hundreds column is digit 2. And the thousands column is digit 3. And so on and so forth. Okay, easy enough. Now decimal is known as a base 10 numbering system. Okay, what do they mean with it? It means basically all of your columns of values, we can arrive at those values by taking the value 10 as the base and then raising it to an exponent that is equal to the position of the digit. So in other words, the ones column is equal to 10 to the power of 0. 10 to the power of 0 is 1. The tens column is equal to 10 to the power of 1, which is 10. The hundredths column is 10 to the power of 2, which is 100. And the thousands column, or the fourth value, is 10 to the power of 3, which is the thousands column. Okay, simple enough so far. Now, how do we then get or prove that a certain value is in fact 5,706? Well, easy enough. You take the value in the positional column, so say for instance 1,000, and then you multiply it by how many times is specified in the number. So in this case, we know that there are 5 in the positional column for 1,000. So it's 5 times 1,000. There's a 7 in the hundredths column, so it's 7 times 100. There is a 0 in the tens column, so it's 0 times 10. And there's a 6 in the ones column, so it's 6 times 1. So to arrive at 5,706, it actually consists of the numbers 5,000 plus 700 plus 6. Okay, simple enough. You'd say, why do I need to know this? Because working in binary is actually exactly the same. So say for instance we are given a binary bit string. This thing is 8 bits long, so it is considered to be a byte or an octet. So the bit string is 11100011. Now let's apply the same process we did with decimal. The only difference is that binary is not a base 10 numbering system, it is a base 2 numbering system. So instead of using the base number 10, we use the base number 2. So we have quite a few columns, and unfortunately in this case they're not exponents of 10, but exponents of 2 are still quite easy, because our first value, equivalent to our ones column for decimal, is 1. The second column has a value of 2. Third is 4, then 8, then 16, 32, 64, and then 128. So it's really simple because in essence, you just keep doubling the values. Now, how do we convert that binary value to decimal? By performing the exact same step we did when verifying the constituent elements of our decimal number. In other words, by saying we have the digit 1 in the 128ths column, so 1 times 28. We have the digit 1 in the 64s column, so 1 times 64. We do the same for 32. There's nothing in the 16s column, there's nothing in the 8s column, there's nothing in the 4s column, it's all zeros. We have a 1 in the 2s column and a 1 in the 1s column. Then similar to what we did for decimal, we count everything up. So 128 plus 64 plus 32 plus 2 plus 1. And that gives you a result in decimal of 227. So in other words, the binary bit string of 11100011 in decimal is equivalent to the value 227. So here's some more examples. If you have a bit string that is all zeros, the calculation is basically that there are no ones in there. Now we basically refer to when there's a 1, we say that a bit is activated, because in binary terms or in machine terms, 1 means true or on. So in this case, no bits have been activated. So in other words, there's nothing to multiply with. So the decimal equivalent of that binary string is 0. And then you can see we're going through a few versions or a few various versions of bit strings. And in each case, we're showing what the result is. Once you get to the bottom, you'll see we have a bit string that consists of all ones. Now, a bit string of all ones means all of the bits are active. All of the bits have been turned on. Now, the decimal equivalent of an 8-bit bit string with all ones is 255. So this should tell you something. The lowest value you can have in a byte is 0. The highest value you can have in a byte is 255. So when writing down something like an IPv4 address or a subnet mask, if you write down a number less than 0, it is wrong. If you write down a number higher than 255, it is wrong. Now you might say, whoa, I've seen some crime and investigation shows on TV where they clearly use numbers that are higher than 255. There's a reason for that. It's similar to what they do in television shows where numbers start with 555. There isn't actually a number that starts with 555 in, let's say, in the US telephone directory. So they're using a number that can't possibly exist. So the same thing goes in these shows with IP addresses. The reason they use these high up numbers is because they are numbers that cannot actually exist. So the show isn't pointing you towards a real IP address. So we've seen how to go from binary to decimal. It's also possible to do the reverse. So say for instance we want to go from the number 172 in decimal and we want to figure out what is its bit string or binary equivalent. So this is really easy. Firstly, go and write down all of the values for the columns, because we know that the values are 128, 64, 32, 16, 8, 4, 2, and 1. Secondly, you must realize that 1 is equal to true, also known as on, also known as yes. 0 is equal to false, off, or no. Okay, so with that logic in mind, we're going to do the conversion by asking a few questions. Okay, so is 128 less than 172? And the answer is yes, which is the same as saying 1. So after we've done that, we've used the 128. So because it fits, we now have to subtract 128 from 172. That gives you 44. So then we ask, is 64 smaller than 44? The answer is no, so we write down a 0. Since 64 is bigger than 44, we don't need to subtract anything, so we'll still use the number 44. So let's ask again, is 32 smaller than 44? Yes, it is. So we write down a 1. Because we answer true, because 32 is smaller than 44, we've used it, so we now have to subtract it. So what is 44 minus 32? That is 12. So then we ask again, does 16 fit into 12, or is 16 greater or smaller than 12? No, it doesn't. So we carry the 12. Is 8 smaller than 12? Yes, it is. So 12 minus 8 is 4. Is 4 greater than 4? No, it isn't. It actually fits into 4. So in other words, 1 and 4 minus 4 is 0. 2 doesn't fit into 0. And 1 also doesn't fit into 0. So our final answer is that the decimal or the binary value that is the equivalent to the decimal value of 172 is 10101100.